Good morning. Today we will be looking at developing and applying formulas for area and perimeter to triangles and quadrilaterals, and we're going to use them to work with the ancient Chinese puzzle known as the tangram. Hopefully, as you review this video, you will begin to see how you can also apply the area and perimeter formulas to construct useful objects in architecture and engineering as well as in art. So enjoy the video. Make sure you take notes on your skeletal outline 9-1. If you need a copy of that skeletal outline, you can see me for it, and it is also on Learn. Good luck, and if you have any questions, please see me directly. Good day. Please take out your skeletal outline for 9-1. You can find it on Learn, where you can download it, or you can obtain it directly from me. Today's objective will be to develop and apply the formulas for the areas of triangles and special quadrilaterals. We're also going to solve problems involving perimeters and areas of triangles and special quadrilaterals. After that, we are going to go on and do the same thing for circles, and then we are going to cover the unit on circles. But right now we're going to travel back to ancient China, and we are going to look at something called a tangram. A tangram is an ancient Chinese puzzle made from a square. The pieces can be rearranged to form many different shapes. The area of a figure made with all the pieces is the sum of the areas of the pieces. And this puzzle was indeed used by ancient classical scholars in the Chinese Empire to assist them in preparing themselves for the many administrative tasks that they had that were important to that empire. The postulate that backs up what we're doing with a tangram is the area addition postulate, postulate 9-1-1. Make sure you get this down. The area of a region is equal to the sum of the areas of its non-overlapping parts. We're going to use this postulate again and again. Here are some examples of tangrams. Here is a common tangram in the shape of a square, and of course its pieces, as you can see, are formed of parallel polygons. In some cases they're squares, in some cases they're triangles, and in some cases they're parallelograms. But with these pieces you can develop all kinds of artistic things, such as the following. And some of these were used in ancient Chinese decoration, and to this day you will find Chinese people who love to use these in something similar to what we call origami in Japanese art, where it carries forward into more modern times. We're now going to examine some formulas. Currently we're going to look at the area of a rectangle, and the common formula is A, or area, equals B, which is the base, times H, which is the height. You can use the area addition postulate to see that a parallelogram has the same area as a rectangle with the same base and height. And if you look at the two diagrams at the bottom, you can cut off the triangle that is on one side of the parallelogram and translate it over to the other side, where it appears that the parallelogram is missing a piece, and that creates a rectangle. So you can see that you have the exact same area in the parallelogram and in the rectangle, which of course is a form of parallelogram. Okay, so formally we can state that the area of a parallelogram, like the area of a rectangle, and of course a rectangle is a parallelogram, the formula for their area is area equals base times height. They use the same exact formula, and that makes sense because remember that rectangles and squares are also parallelograms. So the area of a square, as we know, with a side of S is area equals S squared. And the perimeter equals 4 times S, or 4 times sides. Now we go to S because, again, with a square, since all of the sides are the same measure, we can just use the one variable S for sides rather than have one for base and one for height. Now, one thing you will need to remember when you sit down to try to determine the area of a parallelogram is to make sure that you measure the height along a segment perpendicular to a line containing the base. If you're unsure of how this looks, go back to the previous slide and look at how the height was measured in the parallelogram. Now, when we're talking about the perimeter of a rectangle, you'll again remember that a rectangle's sides have different measurements. So we, instead of using S for side and say that the perimeter is 4 times the sides, we're going to say the perimeter is 2 times the length of the base plus 2 times the length of the height, or P equals 2B plus 2H. Now we can also factor out the 2 in that equation and state that perimeter, or P, equals 2 times, and then in parentheses, base plus height, B plus H, in parentheses. Okay, so in this next series of slides, we're going to cover a problem which I'm going to model you on finding measurements of parallelograms. Then following these slides, there will be another set where I'm going to have you work in groups to basically do the same thing. So please follow along and make sure you take notes on this in your skeletal outlines, and of course any extra pages that you need, use line paper and attach it to your skeletal outline notes. So if you will notice, what they've done here is they've attached a right triangle to the right side of the parallelogram. And if you look at that right triangle, you'll notice that the third side basically is the left-hand side of the parallelogram, which we know should be 34 millimeters. Now, how do we know that? Well, you have to remember that two opposite sides of the parallelogram are congruent. So that third side is 34 millimeters. They give you that one side, which we'll call side A, is 30 millimeters. We just don't know what the height is. That's going to be our B side, but we'll call it H because it's height. So the first thing we're going to do is use the Pythagorean theorem. That's obviously where they're going to with this, to find the height of H. So you're going to use the 30 millimeters as your A squared, so that'll be 30 squared, plus your B squared will be H squared, and your hypotenuse, which is 34 millimeters, we're going to square that, and that'll be your C squared. And when you square those, your 30 squared will be 900, and your 34 squared will be 1,156. And so you're going to subtract the 900 from the 1,156, and you're going to get H squared equals 256. And then when you take the square root of that, of course, you're going to find that H equals 16. Now you notice I talked you through those things. You should know your algebra pretty well by now to be able to do the steps that lie in between these first two equations here that are on the slide. Okay, step 2 then is we're going to use H to find the area of the parallelogram. So we're going to do another whole set of calculations. We know now that the height of the parallelogram is 16, and we know the base is 11. So if our area is base times height, then we're going to multiply 16 times 11, and that should give us the area. So we're going to substitute 11 for B and 16 for H, and we get that the area of this parallelogram is 176 millimeters squared. So it's pretty simple to do this. But to do it, you had to create your little triangle, your right triangle, on the side of this parallelogram, use the Pythagorean theorem to find the height, and then you could find the area of the parallelogram. In this next example now, we are going to again use the formula for area of a triangle, but this time I'm going to give you the value for the area, and what they want you to find is the height, which we're going to call h. And we're going to do this by a simple process of undoing, which means you're going backwards so that you can strip away anything that's around the h in the equation and discover what h actually is, what the height is. So let's do this, and please don't be afraid of the quadratic expression that you see there as what a equals. Let's just put it into our equation and see how we're going to treat it. So the area of a rectangle starts out with the same formula. Area equals base times height. Real simple, nothing hard here. Let's take a deep breath. We're going to substitute. All right, so we'll substitute that 6x squared plus 24x minus 6 for a, or the area. And we're going to substitute 3 for the b, and so we'll have 3h on the other side. So here it is. 6x squared plus 24x minus 6 equals 3 times h. Now, yes, it's a gnarly looking quadratic equation, but we're going to use our pattern identification tools to simplify this a bit so that we can get rid of the 3. That's what we're focusing on, that 3 that's next to the h. Well, look over on the left-hand side. And please note the coefficients for the quadratic expression there are 6, 24, and negative 6. You can factor what out of those? Well, you can factor a 3. And 3 is what's on the other side. So let's go ahead and factor the 3 out of the expression, 6x squared plus 24x minus 6. And you'll see you get 3 times 2x squared plus 8x minus 2. Now, again, when you're factoring, you're undoing. So you're doing the opposite of what you would normally do, which is to distribute the 3 to the 2x squared and to the 8x and to the negative 2. You're just doing the reverse. Piece of cake. It's simple reverse distribution. Now you've got a 3 that you factored out of the left-hand side of the equation, and you have a 3 with the h for height. Well, divide those out, and you'll find out what h is. So let's do that. Divide both sides by 3, and so then you get that h equals 2x squared plus 8x minus 2. Pretty simple. You don't have to go any further, except we're going to reverse these things, and then we're going to say that, this 2x squared plus 8x minus 2 equals h. So we're going to use the symmetric property of equality to just reverse the h and put it on the left-hand side, and there you go. And then, of course, we put the expression, the quadratic expression, into parentheses so that we could say that it was inches, and we put inches afterwards. So our answer is h equals, in parentheses, 2x squared plus 8x minus 2 inches. Simple enough, huh? Okay. You may be wondering why we are finding areas and perimeters of these various polygons when we started out by talking about Chinese tangrams. Well, remember, tangrams are puzzles made of geometric figures, and if you're going to create a tangram, which is one of the things the Chinese did as an intellectual exercise and to amuse themselves, was they had to find the area and the perimeter of these various geometric figures. So that's what we're doing. And in this next example, we're going to find the perimeter of a rectangle in which we are given the area, and that's 79.8x squared minus 42 centimeters squared. We are also given the length of one of the sides. It's 21 centimeters. Now, even though it looks like they're applying it to the base, you'll find that when we get into the problem, they're actually going to apply that to the height, and we're going to be looking for the base. So, step 1 is to use the area and the height to find the base. So let's use, first of all, the area formula. And here it is. Area equals base times height. Now we are going to substitute 79.8x squared minus 42 for the area and 21 centimeters for the height. And our goal is to find the base. So that means we've got to algebraically strip away that 21 from the b for base and we got to do it to both sides in order to figure out what base is. So let's do that. Let's divide by 21 on both sides. Now when you do that, you'll notice 79.8 can be divided by 21 and you get 3.8, and 42 divided by 21 is 2, and this is negative 42, so it's negative 2, and b divided by 21 is b. So we figured out what the base is for this particular triangle. In the next example, we're going to use the base and the height to find the perimeter now. So we're going to look for the distance around the edge of the rectangle. So the formula for perimeter of a rectangle is P equals 2 times the base plus 2 times the height. Well, we know what the base and the height are, so we're going to substitute those. So we'll substitute 3.8x squared minus 2 for the base and 21 for the height. And we're going to get P equals 2 times 3.8x squared minus 2 plus 2 times 21. All right. So all we have to do is simplify here. Multiply both the base and the height times 2. When we do that, we get the perimeter equals 7.6x squared plus 38 centimeters. And that's all we need to do to find the perimeter. Okay, now it's your turn. So please stop this video if you need to. You're in your group, so go ahead and work together and find the base of the parallelogram. And you may want to draw this parallelogram in which the height is 56 yards and the area is 38 yards squared. So go back to the beginning slide, example 1A, and that will again give you guidance for doing this work. When you are done, resume the video and move on to the next slide, and of course make sure you write all of your work down in your notes. Now we're going to move on to triangles and trapezoids. So to find the area of a triangle, you will use the formula area equals 1/2 base times the height. And for a trapezoid, it has 2 bases, if you will. And you'll notice there's a short top and a longer bottom to a trapezoid. So we call those base 1 and base 2, or B1 and B2. And so the area for a trapezoid varies from that of a rectangle, in which we're going to take the the 2 bases, base 1 and base 2, add them together, and then we're going to divide them by 2 and multiply times the height, and that will give us the area of a trapezoid. So in our next example, we're going to find the measurements of triangles and trapezoids. So first of all, let's find the area of a trapezoid in which base 1 equals 8 inches, base 2 is 5 inches, and the height is 6.2 inches. Let's pull out our formula. The area of a trapezoid is area equals 1/2 B1 plus B2 times the height. So we'll substitute for 8 for B1, 5 for B2, and 6.2 for the height. And there you have it. Now you just simplify, add together the 8 plus the 5, take 1/2 of that, and then multiply that to 6.2. And here is what you get. The area is 40.3 inches squared. So not too tough. Now let's do this for a triangle. We're going to find the base of the triangle in which the area equals 15x squared centimeters squared. Okay? So we're going to start with the area of the triangle, and the area is 1/2 the base times the height. And we're going to substitute 15x squared for A and 5x for H, and then that should allow us to find the base. We're going to strip, of course, the 5x and the 1/2 away from B for the base to find out what B is. It's a process of undoing again. Let's just take it a step at a time. It's not tough to do, even though you see a gnarly fraction in there, okay? So divide both sides by x. When you do that, that gets rid of the quadratic issue. And so now you have 15x equals 5 over 2b. Now you're going to ask yourself, why 5 in the numerator? And wasn't it multiplied to the x? Well, remember, the 1 and the b and the 5 all multiply together, so you can end up with 5 over 2b. Now multiply both sides by the reciprocal of 5 over 2, and that's going to get rid of the fraction on the right-hand side and allow us to get b all by itself. So when we do that, b is going to equal, when we multiply and then divide, 6x. Okay. Now let's use the symmetric property of equality and just reverse those, and we'll have b equals 6x centimeters. Not too tough. Okay, in this next example, we're going to find the measurement of a trapezoid. In this case, we're going to find B2, the bottom base side of the trapezoid, which the area is 231 millimeters squared. Notice that over on the side here, they've attached a little right triangle because they want to find the height, and the height is 11 millimeters. Okay? So knowing that, let's put together our area of a trapezoid formula, and that's area equals 1/2 base 1 plus base 2 times the height. Now let's substitute. So we substitute 231 for A, 23 for base 1, and this height that we have, 11, for the H. So 231 equals 1/2 23 plus B2 times 11. We've got to strip all that stuff away on the right hand side of the equation from the B2 to find out what B2 is. So we're going to do the reverse order. We're going to undo. So the first thing we're going to do is we're going to multiply both sides by 2 over 11. Well, why that? Well, all we're doing is multiplying the 1/2 times 11, and we get 11 over 2. Well, then we multiply it times 2 over 11, which is the reciprocal. It gets rid of the fraction, which would be 11 over 2, and leaves 23 plus B2 on the right-hand side. And of course, we've got to do the same thing to the 231. So when we do that and multiply times 2 over 11 and then divide by 11, we get 42 on the left-hand side, and then we get 23 plus B2 on the right-hand side. Now, we want to get B2 all by itself. Now it's just a simple matter of subtracting 23 from both sides, and so B2 is 19. And using the symmetric property of equality, we reverse the B2 and the 19, and B2 equals 19 millimeters. Okay, your turn again. I want you to find the area of the triangle to the right. So you're going to use the area formula, use the appropriate example that we showed you before, and please solve this in your notes. And then when you are done, please move on to the next slide. Oh, before we do that, we're going to find B, and I'm going to give you that information. So B squared plus 12 squared equals 20 squared using the Pythagorean theorem. And substituting, we're going to find that 12 squared is 144 and 20 squared is 400. So B squared is 144. B squared plus 144 equals 400. And then you subtract 144, you get B squared equals 256. And then take the square root of 256, and B equals 16. Now you will need to take that information, now that you know what B is, and find the area of the triangle, and I'll let you do that on your own. All right, remember that the diagonals of a rhombus and a kite are perpendicular, and the diagonals of a rhombus bisect each other. Now, why are we going to talk about those? Well, obviously, we're going to be examining the areas and the perimeters of those particular figures. So let's take that information and move on. Okay, now let's look at the formula for the area of a rhombus or kite. Well, because we have those diagonals we talked about, we're going to call them D1 and D2. So the area of a rhombus or kite is 1/2 times d1 and d2. Let's apply that now to this example, finding measurements of rhombuses and kites. So we're going to want to find d2 of a kite in which d1 is 14 inches and the area is 238 inches square. So let's get our formula out. The area of a kite is 1/2 times d1 times d2. Let's go ahead and substitute 238 inches squared for area and 14 inches for d1. And there you have it. Now we're going to solve for d2. So again, we're going to undo and strip away the 1/2 and the 14 and get d2 by itself to find out what d2 is. So let's do that. So solve for d2. Well, if you take half of 14, that's 7, and you're going to divide by 7 on both sides, and so you're going to get 238 divided by 7 is 34, and that's the answer for d2. Pretty simple. And using the symmetric property of equality, you can reverse those and say that d2 equals 34. Now let's find the area of a rhombus. So in this case, you have a rhombus, and you're told that d1 is 8x plus 7 centimeters, and d2 is 14x minus 6 centimeters. Let's apply the formula. So the area of a rhombus is, again, area equals 1/2 d1 times d2. Now let's substitute. So we're going to substitute the two diagonals, and this time we're going to find the area. So you've got area equals 1/2 8x plus 7 times 14x minus 6. So here you're going to have to do some distribution and multiplication. And you know what? This looks suspiciously like we might get into quadratics land. Let's see if we do. So multiply the binomials using FOIL. Remember what FOIL means. First, outer, inner, and last. So yes, indeed, we're going to multiply 8x times 14x, and we're going to get an x squared number. Then we're going to multiply 8x times negative 6, and then 7 times 14x, and then 7 times negative 6. And then lastly, we'll divide that by 2. So let's do that. So you get 1/2 times 112x squared plus 50x minus 42. Now, divide by 2 and distribute. Well, basically, when dividing by 2 is multiplying times 1/2. We're going to distribute that 1/2 to each of the terms. And so let's do that. Multiply 1/2 times 112x squared, and 1/2 times 50x, and 1/2 times negative 42. And you get that the area equals 56x squared plus 25x minus 21 centimeters squared. Okay? So again, don't be afraid of quadratics. All right, now let's find the area of the kite over here. So again, let's use our area formula for a kite, which is the same as that of a rhombus. Notice we have 29 inches for one side and 35 inches for another side. And it looks like x is 28 inches. So let's examine this. So step 1, the diagonals d1 and d2 form 4 right triangles. We're going to use triangles. So let's use the Pythagorean theorem to find x and y. So 28 squared, that's one side of a triangle, plus y squared equals 35 squared. Now, square those numbers and subtract the 28 squared from the 35 squared, and you get 441 after you square them. And of course, take the square root and you get y equals 21. So now you have one diagonal solved. Now, go ahead and do it for x. So 21 squared plus x squared equals 29 squared. And again, after you've squared 21, you subtract that from the square of 29 squared, and you get x squared equals 400. And of course, take the square root of that, and you get x equals 20. You now know what x and y are. Next step is you're going to use d1 and d2 to find the area, because that's where we want to go with this. So d1 is equal to x plus 28, because x is only 1/2 of the diagonal and 28 is the other half. And that would be 48. Half of D2 is equal to 21, so D2 is equal to 42. So the area of a kite, use the formula, area equals 1/2 D1 times D2. And substitute 48 for D1 and 42 for D2, and you get the area equals 1/2 48 times 42. Now simplify. And you'll get the area equals 1008 inches squared. All right, your turn again. So I want you to find D2 of a rhombus in which D1 equals 3x m and a equals 12xy m squared. Okay, so use the materials that you looked at just previously that I modeled for finding the area of a rhombus to get this information. Stop the tape if you need to. Do your answers together in group, and then when you're done, make sure you've written them down in your notes, and then move on. All right, this last example is an application example of a game. And you'll notice you have tiles here, and the tiles form a rectangle where the base is 4 inches and the height is 2 inches. Now, you're going to use the grid to find the perimeter and the area of the leftmost shaded parallelogram. So you'll notice there are parallelograms, some are shaded and some are not. All right, so for perimeter, two sides of the parallelogram are vertical, if you look at the parallelogram that's shaded, and the other two are diagonals of a square of the grid. So each grid square has a side length of 1 inch. And since you're given that information, then the diagonal is going to be the square root of 2 inches. The perimeter of the leftmost shaded parallelogram then is going to be p times 2 times 1 plus 2 times some unknown equals 2 times the square root of 2 inches. Okay? All right, so what I want you to do now is examine these tiles further so we can find the area. And as I said, the tile design shown is a rectangle with a base of 4 inches and a height of 2 inches. So we're going to use the grid again to find the perimeter and area of the leftmost shaded parallelogram. So for area, the base and height of the leftmost shaded parallelogram each measure 1 inch. So the area equals base times the height, which equals 1 times 1, or 1 inch square. Okay, it's your turn now. As the last act for today, you are going to find the area and perimeter of the green triangle in the tangram that you see below. So we're back to tangrams, which is where we started. And so all of you, as your ticket out of here, you will figure out the area and the perimeter of the green triangle at the base. And you should note that each grid square has a side length of 1 centimeter. So use your formulas for area and perimeter to solve this particular problem. And make sure you put it in your notes, and then we will report out at the end. Thank you very much.